Okay, thank you very much everybody for coming, and thank you Robin and Clarissa for organising, and Len for welcoming us here this evening. I carry out research on the nature of time, and what I'm going to do is tell you a story that sort of gets you to the point at which my research begins. And my story about time starts with Newton's conception of time. So I'm going to tell you a little bit about Newton's conception of time. I'm going to give you a crash course in the special theory of relativity in under 2 minutes. And then I'm going to take you into the strange and very interesting world of quantum gravity, which makes use of time and has some very interesting things to say about time as well. All right, let's see. Okay, we're going to start by exiting the slideshow. Okay, we're going to start with a Newtonian conception of time. So here's what Newton said about time in the Principia Mathematica. He said, absolute, true, and mathematical time of itself and from its own nature flows equably without regard to anything external. So what have philosophers taken away from this? Well, what we commonly see Newton as giving us is a kind of understanding of time as we might experience it at an everyday level. So what we seem to experience when we look around the world and carry out our lives from day to day is a picture of time where everything's sort of happening in a line, as it were. We're sitting here enjoying our meals, listening to a lecture. Later on, we'll be enjoying dessert, and then later on, you'll be heading home. And then later on, much later on, you'll grow old, and much later on, you'll pass away, and then other people will come into existence, and so on. As events in the future come closer and closer towards us, we anticipate them arriving, and then they sort of pass through the present, and then they slide into the past, into the dim reaches of history. What's crucial about Newtonian time is that there is just sort of one tale to tell about the nature of time. And in particular, there's just one way to take all of the events that exist in our universe and order them in terms of which events happen first, which events happen second, and so on. Right? So Newton thinks that there's just one way to order time. And this is where this metaphor of flow comes from. You have a wave of time that sweeps across the entire universe, catching everything in its wake. But it catches everything in its wake in exactly the same way. Right, that was Newton's conception of time, and Newton did a great deal with this conception of time. Once Newton adds time into his mechanics, we get the ability to predict the orbits of planets and celestial bodies. We get the ability to do all kinds of interesting things with engineering, mathematics, and physics that we couldn't do before. Right, so Newton's time gets us quite a long way. Unfortunately, in about the early 20th century, we quickly discover that there's something deeply wrong with Newton's conception of time. And this is the point at which time starts to stand still. From this very much dynamic conception of time that Newton gives us, where time is this thing that flows equably without regard to anything external from itself, we get this new kind of static picture of time, which Einstein gives us. And now being static is not its most surprising thing. And in order to understand the surprising nature of Newtonian time, Einstein's time, we're going to have to get a little bit of a sense of how relativity works. So, if I can, what I'm going to do is I'm going to, in order to set the scene for a crash course in relativity, I'm going to show you a quick video, hopefully, if this will work. Oh. No, I'm going to have to Google this video very quickly. From the Mythbusters website. Cannonball cancel. This is research in action, folks. And in order to see just how weird light is, what we're going to do is we're going to think about something that's not light at all. And in particular, we're going to look at a cannonball. So this is an experiment that Mythbusters carried out, which is supposed to give you an insight into the mechanics of various moving objects, and in particular the way that you can cancel the motion of a moving object. So if you're driving along in a truck and you shoot a cannonball out the back of your truck, there's a speed at which you can travel that will cancel the motion of the velocity of the cannonball exactly, such that the cannonball just sort of stops and drops in its place. And that's what these guys do on Mythbusters. So let's see how this works. It's a pretty cool thing to watch.
To a perfect demonstration. We're going to see that ball drop. With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down. Dude.
Woo! We did it! We did it!
Okay, so that's what you can do with cannonballs. One of the really creepy things about light is that you can't do that. If I shoot a laser out the back of a truck, moving at any velocity, I can't cancel the motion of light. I can't make a light ray or light particle or photon or wave, whatever it is that you think light is, just stop and fall. If I shoot a laser out the back of a truck and the truck is moving at 10 kilometers an hour, the laser's going to shoot out the back of that truck at 300,000 kilometers per second. If I'm moving at 200 kilometers per hour, that laser's going to shoot out the back at 300,000 kilometers per second. This is one of the amazing things that we discovered in the early 20th century, was that light, no matter how fast you're going, travels at exactly the same speed. It travels at 300,000 kilometers per second, so you can't cancel its motion. And what this means is that we have to completely rethink the way in which we order events. Our understanding of what it is for two events to happen at the same time is based primarily on the way that light behaves. If I want to know whether two lightning strikes, for instance, occur at the same time, how am I going to do that? Well, I'm going to stand in a particular spot, I'm going to look into the night sky, and I'm going to see the flashes, and I'm going to wait for the light to hit me. If the light hits me at the same time, if the two light rays collide with my perspective together, then I'll see the lightning flashes happening together. I'll say they happened at the same time. If the light from one lightning strike hits me before the light from the other lightning strike, then I'll say that the lightning strikes didn't happen at the same time. Okay? That's enough to completely revolutionize the way that we think about time. And Einstein did this in a series of papers, but the very first time he does it, he actually does it using a thought experiment, which is something that we use in philosophy in order to understand things when we can't carry out real experiments. And we can't carry out this experiment, and so far as I know, no one's been able to conduct this experiment as Einstein stated it, because you need to be able to make something travel at about 150,000 kilometers per second, which is quite fast. If we could make things travel at that speed, we'd be able to get to the moon in a very, very short amount of time, but we can't. So we can't actually carry out this experiment, but it's very simple to think through the experiment. So here's how the experiment goes. We've got two people, a person on a train, and that person is traveling at 150,000 kilometers per second, so they're traveling at half the speed of light. And we've got a person on a platform watching the train go by. And what happens is that lightning strikes the two ends of the train. Here's what the person on the platform sees. They see when the lightning strike the two ends of the train, they're standing equidistant between the two ends of the train, and so they've got the light rays have the same distance to travel from the two ends of the train to them. So what do they see when the lightning strikes happen? Well, they see the two lightning strikes happen together at the same time, because the light hits them together. The person on the train, though, that person is chasing down the light ray that hits the front of the train, and they're running away from the light ray that hits the back of the train. So what that means is that they intercept the light ray coming from the front of the train before the light ray from the back of the train hits them. So, from these two perspectives, we get two very different determinations of when these lightning strikes occurred. The person on the platform says, the two lightning strikes are simultaneous, they happen together. The person on the train says the lightning strike that hit the front of the train occurred before the lightning strike that hit the back of the train. Okay? So here we've got a disagreement about the ordering of events. One person says the two events happened together, the other person says that one happened before the other one. Now, if we could say that one of these people is correct, that one of these people has the sort of facts about when things occur available to them, then we wouldn't need to be worried. We could say, look, the person on the train, Susie, she's just mistaken about when these two lightning strikes occur, whereas the person on the platform, Billy, he's got the facts of the matter about when the lightning strikes occur, or vice versa. That would be very nice, except that we can't do that. There is no physical reason to suppose that what happens for Susie is correct or privileged or somehow special compared to what happens for Billy. In other words, they're both correct. There's no physical way to split the difference between them. Now that's a sort of very particular notion that also turns up in the special theory of relativity, and that notion is sometimes called Galilean relativity. It was known at the time of Galileo, which is that no matter how fast you're traveling, the laws of physics behave exactly the same. Right? So you don't observe differences in the laws of physics based on your relative motion. So if you speed up, and you drop a cannonball, that cannonball is going to drop in exactly the same way as if you're traveling slowly. Okay, if you put those two things together, namely the fact that when you are traveling, the laws of nature work exactly the same, you can't get any sort of physical difference based on your relative motion, with the fact that light is always going to move at the same speed no matter how fast you're going, and you end up with this result, and you end up with no way to break the symmetry between Billy and Susie. There's no way to say that Billy is right and Susie is wrong. There's no way to say that Susie is right or Billy is wrong. Right? We've got no way to split the difference here. And that is the foundation for the special theory of relativity. Those two things, the speed of light is the same no matter how fast you're traveling, and the laws of nature are the same no matter how fast you're traveling. Those are the two core postulates that underwrite most of special relativity and indeed get you into full-blown general relativity later on. For our purposes, all we need to focus on is the following fact. These two guys, they disagree about the distance, the temporal distance between events, the temporal ordering between events, and there's no way to settle that dispute. Okay. So what this means in sort of full-blown relativity is that the ordering of events depends on how fast you're going. As you speed up, events change their ordering. So what is happening now and what is happening in the future and what is happening in the past depends on how fast you're going. Travel fast enough and the entire future might just become present for you. Travel fast enough in the right direction and you might be able to loop back on yourself and travel back in time. Right? So, I mean, this is completely shocking. We have this idea of time as something that is, inalienable, absolute, flowing forth, but it turns out to depend on how fast we're going. And if we want to change the facts about time, we just need to speed up or slow down. All right. That gets us to Einstein's relativity. Now we're going to come up to present-day physics and one of the big mysteries, if not the biggest mysteries in physics. And the mystery is this. We've got two current physical theories that it's fair to say are the best theories that we have available to us. General relativity, which takes the lessons learned from special relativity and extends them to give you an account of gravity. Exactly how that works is not important. All you need to know is that it treats time the way that special relativity treats time, as something that depends on how fast you're going. And then we've got quantum mechanics, which is our other most successful theory. General relativity is our best theory of the very, very big, and quantum mechanics is our best theory of the very, very small. Quantum mechanics uses Newton's conception of time. General relativity uses Einstein's. General relativity and quantum mechanics are incompatible with each other. We have no theory that reconciles our two best empirical theories ever created. And so we end up in a situation where we have this thing called the problem of time. We have two competing conceptions of time and no way to reconcile them together. If we want to reconcile these two things, we have to produce a theory of quantum gravity, which is a theory which takes the lessons from general relativity and applies them at the kinds of scale that quantum mechanics is interested in, the scale of the very, very small. That would be very nice. Maybe you've heard of string theory. String theory is a theory of quantum gravity. It's a way of reconciling these two theories. All such theories make predictions at scales that we can't experimentally test. So we have no idea whether any of these theories are true. Some of these theories, and this gets you to the kind of research that I'm interested in, some of these theories solve this problem in the following way. Time is the problem, so let the axe fall on time. Let's just remove time entirely. There's a whole class of theories of quantum gravity, which are so-called timeless theories of quantum gravity, which deny the existence of time entirely. A number of physicists have made this claim, time just doesn't exist. As a philosopher, I'm completely unsure as to what they mean. And so what I'm in the business of doing is trying to interpret these physical theories. What is it to say that time doesn't exist? If time doesn't exist, what would that mean for our everyday lives? Would we have to take the history department and say, sorry, but everything you're talking about actually is completely wrong because there's no such thing as time? Right? And not just history. I could walk into evolutionary biology and say the same thing. I could walk into archaeology, art history, you name it, and it goes out the window if we lose time. So if what these physicists are saying is right, then the implications are extremely radical. Now, as philosophers, what we try and do is mediate some of the interesting things that physicists say with some of the things we might actually believe and try to come up with some halfway house. And that's what I'm trying to do. I have no idea how to do it. I know that it's very hard. And so stay tuned. Thank you.